right, Math 281 students, good to see all of you. I'm back in our usual conference classroom here, and on Wednesday I didn't quite get a chance to finish absolutely everything I wanted to say about topology. Boy, there's so much we could say about it. I could probably talk forever about it. I really love the subject, but I'm just going to do a little bit of an extra piece here for you because there's a couple of questions on the homework that have to do with open sets, and I didn't quite get a chance to explain what that means. So I'm going to do that really briefly, just a short video here. When we ran out of time on Wednesday, I was talking about neighborhoods. And a neighborhood really consists of a point and a positive integer p. And you're in some metric space, and you're looking at all of the elements of the metric space x that are a distance less than p away from this point x naught. So x naught is just a fixed point of the metric space, capital X, and you're looking at all of the other points of that metric space that are close to x naught, within p units of x naught. So we did this on Wednesday. There are several examples. If you go to the classic real number line with the absolute value metric, right, that's kind of the most familiar example, then your neighborhoods just look like open intervals, right? Every time you pick a point x naught here, the radius of the interval being p on each side of x naught, that open interval, it's an open interval there, that I've highlighted here in blue, that open interval is a neighborhood. And so all of the neighborhoods kind of look like that. If we go to the whole xy plane and we use the Pythagorean metric that we talked about, well, now if we fix a point here, x naught, y naught, right, somewhere in that xy plane, then the neighborhoods look like disks. These are open disks. They do not include the boundary. You're looking at all of the points that are within p units of the center, which is centered at that point x naught, y naught that you have fixed. Okay. And finally, we looked at this taxicab metric. If you take any set and you define the distance between any two distinct points to be equal to 1, well then there's only two types of neighborhoods you can get. If your radius p is 1 or less, then the only points that are in the neighborhood of x naught of that radius will be x naught itself. Okay? All of the other points are too far away. But if your radius is more than 1, then since all points are within 1 unit of each other, right, the distances are never more than 1, then the entire set x would be a neighborhood in that case. Okay? So this is the definition of a neighborhood, and we need this concept of a neighborhood to define what's called an open set. Okay, so I'm going to start right here, and this is where we get into something I did not get around to saying on Wednesday. Okay, so this is a definition, okay? A subset U of capital X is open. Okay, it's an open set if for every little x in U. So if you take every single point of the subset, all right, there exists a positive integer p. This is the radius of our neighborhoods that we've looked at before. There exists a positive p such that the neighborhood around x of radius p stays inside of U. It is a subset of U. Okay? So what we're saying is that every point of this open set has to be such that you can build a neighborhood around it that is still completely immersed within the set. Okay? So for example, if we look at an open interval here, if I take any point of this open interval, let's say pick this point x right here, okay, what I can do is I can build a neighborhood. Let me draw a neighborhood around it. See, I can build a neighborhood around x right there that stays completely within the big blue interval that we originally had drawn in here. Okay, In fact, you could figure out for any given point in that big blue open interval, you can figure out how big of a radius P you can take so that the neighborhood around that point stays within the big blue interval. Okay? So those open intervals, those would be a good example. That's a good example of an open set, right? So open intervals are open. Well, kind of that's why we call them open, right? Okay, so just as an example here, the interval, anytime you take an interval, AB, is an open subset of the real numbers with the absolute value metric. Okay, so if we use the standard example here, then anytime you take an open interval and you pick a point within that open interval, you'll be able to build a neighborhood. Might be a very small one. P might not be very large, right? But there will be a P, a radius that you can build around that point that keeps that neighborhood within the set, within the open interval AB that you started with. Okay? Hopefully that kind of makes some sense. Let me just give another couple of examples. I mean, in terms of kind of a two-dimensional visualization here, right? We think about R squared. You think about R squared, right? Basically, inside of R squared, let's say I have a set that looks like this, and I've dotted the boundary of it. The idea being that if you pick any point on the inside there, okay, and let's say you use the Pythagorean metric, okay, well, what you can do is you can just choose a radius around this point that keeps the whole disk, that's that open disk neighborhood we talked about, keeps that open disk inside of U, okay? And even if you pick a point that is very, very, very close to the edge, you'll still be able to put a little tiny neighborhood around that point that stays completely within the set, okay? Now, if you include the boundary, if you decided to include the boundary here, it's not going to be open, is it? Because if I take, remember, this has to be for every x in the set. So I could pick my x right there on the boundary of the set. And if I include the boundary as part of the set, well now, no matter how small of a disk I try to draw around that point, that disk is not staying completely inside of the set U, right? It's slipping outside. Right? There's some part of that disk that's outside that set U. So this would not be open. Okay, so this is open here. This one would be not open. Okay? So that's just another example. What about... So that's just kind of a visual example. What about if we go back to x being any set, and we use D to be the taxi cab metric? Okay. Question might be, which subsets of capital X are open? Okay. Well, turns out, if you let U be any subset of X, right, then U is open. Let's see if I can convince you here. Okay, every subset of X is open if you use the taxi cab metric. If you remember, that's the metric where all distances are equal to 1. All right, between any two distinct points, the distance is always 1. Right. Well, here's the reason. You take any subset of X, and you take any point, every X, you take every X within that set, right? Then look what you can do. You can take the neighborhood. Remember, you're allowed to produce the P, right? You get to choose what radius you're going to take around this point X. And if you choose a radius of something that's, say, less than 1, right, then this neighborhood, we talked about it earlier, is just the singleton point X. It's just X by itself. And that surely then is, of course, contained inside of U, which is the requirement that we have right here. Okay, so that's actually a pretty easy thing to see. So every subset of a metric space is open if you use the taxicab metric. Okay. So those are just a few examples of open sets. Hopefully it's kind of enough to get you thinking about the homework. Of course, if you have any questions about it, want to run anything by me, by all means, stop on by or send me an email and ask me a question. I'll be more than happy to help you out. Okay, thanks guys for watching. I appreciate it.